the notification of the recording? Yes, okay, we
Yeah,
are on.
it's being recorded. Thank you.
Okay. So I feel HBase, HDFS is like the Windows, like the platform all other applications sits on. All other say applications of MapReduce make use of HBase as HDFS as the platform, as the foundation. That's why you see said the foundation of efficient data processing in Hadoop is in the data storage model. And the data storage model we are working with is HDFS. And another thing is HDFS is Hadoop implementation of a distributed file system. So as I said earlier on, HDFS is like Windows. How will you view data on Windows? How do Windows operating system interact with data? Do you know when you open data on Windows, you don't have privileges. You don't have like, okay, read write privileges. Okay, this person, we don't have something like the first user, or let's say the owner, the first user, or probably the secondary user. We don't have that in Windows. Anybody can copy, anybody can execute, anybody can do anything. But in Hadoop distributed file system, HDFS, we are able to understand that, see, you cannot just come to my window, to my environment and do anything you feel like. Privileges were given to each file. So to each file, there's a level of privilege or privileges that is assigned to them. So if an application is connecting to a file or is making use of a file on an Hadoop on HDFS platform, and you are not given the right privilege to relate with that file, then you're going to have process failure. I know maybe during our first or second class, or maybe this should be, maybe when we get to our practical session, you're going to see where you grant privileges to files. So where you say, okay, the second user to this file should be able to read it, should be able to write it, or should be able to execute a particular, perform a particular operation on a file. So like I said, HDFS is like the platform, is like the motherboard, and all other applications sits on its HDFS. It is just like a word called distributed file system. It is the one that tells you, okay, you are distributing this way and the likes. So that's that. So I said the third point, introduction, is it is based on the design of Google file system. So I know during our first introduction to big data analytics, we talked about the history of Hadoop, and it came about as a result of challenges faced by Google and Facebook, and they felt like, okay, we need to find a way to distribute. We need to find an efficient way to optimize our database, and they came up with the Google, the Hadoop, the distributed file system. So this is called Google file system. So, but here now we now have an open source um, big data platform that it's called Hadoop distributed file system, and he said it is designed to hold large amount of data. So when I mean large amount of data, so it is very flexible and it can scale. So he said the last point, he said it provides easy access to data to many clients distributed across a network. I think this is the key functionality. So have you guys thought of when you go to your Gmail account and you are looking for a mail that was sent to you some months ago, maybe even 3 years ago, and you go to your mail and on your search button and you just search, okay, maybe you are looking for an invoice receipt that was sent to you some months back, and just type invoice from Google, and in less than 3 seconds, you just see those files being selected. Do you understand? Can you imagine that we have millions of users on Google? How is the search engine being able to identify your own? And how is it being able to optimize the search engine such in a manner that the information you are looking for comes out first? So it is a distributed that said many clients, lot of people can be accessing a file at the same time. It's like it is. Blessing will say it is well. You can have thousands of partition on HDFS. You can partition on hundreds of variable. That's the beauty of Hadoop file system. A lot of clients can interact with it and nobody will be affecting each other. So far your internet is connected, so far you're connected to the database, the process is optimized. One person query is not affecting another person's query. Okay, let me tell you something in real life. If you are working on Oracle, let's say Oracle. Okay. Please let us go. Please be on mute. You're getting a feedback from your hand. Okay, I was saying something. I said, Oracle, you can run multiple select statements on a particular table. So different people at different time can be running select statements on a particular table. And that's what happens in the bank. So, okay, don't let me go into the banking industry. So like, okay, on the same table as Sunday is selecting, Oluwatobi is also selecting on the same table, they are interacting with the table on different interface. So there's something that is created at the back end. They call it session. So sometimes we have limited session whereby it's okay, the total number of sessions that can run in parallel on a particular table is just 150 session or a particular script. So when the limit of that session is reached, any other person that wants to run a select statement or run a session on that schema or the user or the table is going to tell them, see, okay, no session available again. So, but in terms of HDFS, we can have multiple people running queries at the same time. Do you know why it's happening like that? Because like one of the characteristics of HDFS we studied in time past is the data sets, they are replicated on nodes. So there are replications happening on different nodes. So they don't have issues. And there's this ability they call caching, whereby you're able to store the data into a temporary memory space, and it's going to make it accessible to everybody. And like what we said last, like that should be last week Friday. Parallel computing also aids this because everything is in memory. Everybody can connect to the memory, and they run their query and they get the result as fast as possible. So that's fine. So that's HDFS for you. Keep something in mind. I want us to have a picture. It's like Windows operating system. Every other thing sits on it. Okay, fine. Advantages. I said it can store a very large amount of data and support much larger file size compared to distributed file systems such as NFS. Okay. Has anybody heard of this NFS before?
Yes.
Have you heard of NFS before? Yes.
Yes, sir.
Yeah. So I think I understand this better, but I remembered when I started back then when I was doing my computer engineering class, and when you want to install maybe Windows XP, it's going to tell you the kind of partition you want. I know we have NTFS and NFS, something like that. It's going to tell you those kind of partition. So those partition is telling the window the kind of file system that should be inputted on the drive, that should be installed on the drive. So we understand that then that some file system corrupts faster than the others. So like what we are seeing now is Hadoop 2 is like a platform that every one of them sit on, but it is faster than the normal file system such as NFS or NTFS. I said it is designed to spread the data across a large number of machines. We can't overemphasize this, that ability to replicate data across different machines. Please and please keep this in mind. If you picture it as HDFS, Hadoop Distributed File System, as like a window operating system. A window operating system can only be installed on one machine at the same time, just one machine. But now just imagine a particular application that can interact with different machines. Just one system, one operating system, but can communicate with different machines independently and can interact with them. It has the ability to manage multiple systems, but normal Windows can only manage one system at a time. So that gives HDFS the ability to distribute his work. He has the abilities like the father of every one of them. He knows how to interact to every member of the nodes, like each node. Okay, I'm having like 5 nodes, but he's going to have like the master nodes, like the central processing. But to all the other named nodes, he has the ability to communicate with them and share responsibility with them. Are you getting me? So he said the third one, advantage, he said it can store data reliably and cope with malfunction of loss of individual machines. So talking about seeing it as a window in a Windows perspective, as soon as it is communicating with other machines, if any of the machine goes down, he understands that, okay, I'm coordinating, okay, 5 slaves. I have one master, 5 slaves. So he understands, and his tentacles are able to manage the 5 slaves. But if any of the slaves goes down, he also knows, because there's a trigger that sends a message to the master slave that say, master node, that say, okay, see, one of the nodes is down. Now you're only working with 4 nodes, and the system the process is able to adjust on the fly. And when he discovered that, okay, my other nodes are back up, he's able to adjust seamlessly and assign jobs to them. That's something very beautiful about HDFS. It can easily integrate with Hadoop MapReduce, thus allowing data to read and process. Okay, so allowing data to be read and processed locally. So what this means is that as soon as HDFS is able to communicate to, say, 5 slaves, different jobs, different data block are sitting on different node replicated. When a job is sent to node 1, node 1 does not need to work on the master node. Node 1 will work on its own system because it is distributed. After node 1 gets the job done, it will now send the result of the job, to the master slave, the master node, for aggregation. So when jobs are distributed, all of them work independently. When the result is ready, they wait for each other. And the reduce function gather all the jobs, push it to the master node, and the master node display it. So the machines can work independently. So that is why if a machine goes down, it doesn't affect the rest, because they are independent. It's just that they're on the same network. So that is, see, this thing, they are like the core building blocks of Hadoop. Okay, so let's go to the limitations. So everything, there's a limitation. So the first limitation is, HDFS is not a general application and is restricted to particular class of application. So not all application can run on, okay, for instance, now, if you're having a Linux system, not all applications are Linux enabled. If only the application is written to sit on Linux environment. So likewise, HDFS is not a general window that any application can interact with. HDFS has its own rules and regulations. It has terms and conditions. So if you are not meeting, if any application is not meeting the prerequisites for the Hadoop capability, that application cannot work. So, and any application that will be sitting on HDFS must have the distributed file system capability, must be able to distribute jobs. So that is the main thing. So not all applications can work on it. I said HDFS is optimized to support high streaming and read performance, and this comes at the expense of random seek performance. So you won't enjoy HDFS if you don't have high streaming read performance. Like when you are reading data into the process, the stream needs to be massive. I said sequential reads are preferred ways to access file HDFS. So talking about the sequential read, so it must be sequential if you want to access HDFS. So maybe in the later class we are going to understand HBase, and we are going to understand this word better, the sequential read. So whereby it set priority. Okay, which one is coming first? Okay, so it puts order to the read and write, especially to the read. It puts order to it. It said, and the fourth one said HDFS supports only a limited set of operations on files, but not any update. So there's a limited set of operations you can run on a particular file. So if you want to run more operation on the file, you need to take it away from HDFS environment. So the question is, what kind of operation can you run on HDFS that you can run? Like I said earlier, HDFS will give privileges to file, but Windows, you can do anything with any window file. As soon as the file is on the window environment, either you copy, you delete, you truncate, just with one click you can do anything you like. But on HDFS, you have limited operations. You can't just come one day and say, okay, I want to do these things without the right privilege. You can copy file from one folder to another folder, execute from one folder to another folder on Windows. But HDFS, you can't just wake up one day and say, okay, I want to do this without the right privilege. He said, and the last one said, HDFS does not provide a machine for local caching of data. Yes. There's something that reduces latency, and that is caching. But HDFS does not provide, say, a local machine for this. Because of the optimum process of Hadoop, there is no particular system that will catch the queries that were previously executed. I said, okay, we've executed a query, and okay, let's keep it somewhere so that when any other person comes back the next time, we can retrieve it from the cache. It doesn't apply to HDFS. There's no, so far everybody is going to work on his own. So it's very difficult for it to cache. And if other version of Hadoop will be working on caching, then it's going to be a lot of work. So, but for now, there's no local machine that is doing that. Okay, we are going to run very fast. I'm moving forward. The data storage in HDFS is implemented as a block structured file. So block of file. So I used to mention Oracle because that's what 30% of, let's say 60% of what we do on most of our sites works on. There's what we call data file in Oracle, and your maximum data file capacity on Oracle is 32 gig. But on HDFS, the maximum is 64 MB. So why is it like that? So because the smaller the size, the system can easily process it very fast. But on Oracle, we have one data file is as big as 32 gig. That's the maximum. But here, the maximum is 64 MB. So you can see, even if you should load a file of 100 MB, the file system will break it down into bits and say, okay, the first file system for this guy is the first 64, and the rest maybe 30, say 36 will be kept on another file system. HDFS is implemented as a block structured file system. Individual files are broken into blocks. Yes. Okay. So the data file on Oracle is same as blocks. So each block is very small, like 64 MB. Said individual files are broken into blocks of file fixed size, which are stored across Hadoop clusters. A file made up of several blocks. So when you have a file, I'm saving a file of 34 MB, like 100 MB. It will be breaking down into blocks. So a file is making up of different blocks stored in different nodes, choosing randomly on a block by block basis. To improve throughout the data nodes, uses heuristic to determine the optimal number of files per directory and create subdirectory appropriately. So when we get to the practical class, you understand this, and we'll be able to take this into more details. But we are just trying to understand how Hadoop stores its file. So the name nodes ensure that the metadata in the HDFS remain constant. Sorry? Said the name node, that's the server, like the central processing. It said ensure that the metadata, so it knows which block is sitting on each. It knows the address of each. To me, I call metadata address. So I know that Mr. A is living at street 1, number 2, street 1, house number 2. So that is something about the storage. And said, does HDFS implement a master-slave architecture? I think we've seen that we have the master nodes and we have the slave nodes. Okay, so the architecture. So the name node. So when you have, are you guys seeing my mouse?
Yes, sir. Yes, sir.
All right, thank you. So when you have this guy, you have a client data, you have data. Said, okay, I have this data, read it. So when you are reading, the address of the data is kept in the name node. That is the metadata, the description. Keeping in mind that your data is already broken down to pieces. So each piece, each block, because each piece is called block. So each block of the file you loaded has an address. So they are distributed randomly on different nodes. So you can see that this same, like I have 100, let's say I have 1 gigabyte of data. So all the 1 gigabyte of data are broken down into blocks of 64 MB each. So just as if say, okay, 1 gig divided by 64 MB, I know at least we should be having like close to 15 blocks or 16 blocks of data. So those 16 blocks, and you have 3 data nodes. So those 16 blocks are randomly distributed across different nodes. You see, node 1 is speaking 1 and 4 alone. Node 2 is speaking 1, 2, 3, and node up to node n 1, 4, 3. So and you see that there are replications, like node data file 1 is replicated, 4 is replicated, 2 we don't have to replicate it, but each block is replicated on at least 3 nodes. If you have more nodes, so if you have like almost 10 nodes, so at least, because if one node is down, so that the other nodes that has a copy of the file can pick it up. Said for every block, HDFS metadata name replaced. So for every, the HDFS, the metadata for this guy. So what I see as metadata is, okay, when I want to run a process or maybe a map reduce, the name nodes on the metadata, the name nodes understand that block 1, I have block 1 on name node 1. I also have block 1 on name node 2. So the process will now decide, okay, if I want to compute a map reduce, or if I want to run a particular operation or a process, okay, the master node, the name node is now responsible to say, okay, use the block 1 on name node 1, not, so it's going to use, say, block 1 on name node 1, not block 1 on name node 2. You can now say, okay, go to name node 2 and use block 3. So the name node see to these processes, and that is where Jan comes in. That is yet another resources negotiator. So is the guy responsible to making sure you assign task to a particular node, making sure that, okay, the task you are giving to this name node, to these data nodes, the corresponding file system that we use for the operation is sitting on it. Okay, data replication. So we've talked about replication. Hello?
Yes, sir. It's Adequate. Good afternoon, sir.
Good afternoon.
Yes, sir. I just want to ask a question. You said block 1 on node 1. I thought it should be data node. I thought the blocks are on the data node, not the main node. Since the main node is like the main server. So probably I'm confusing some things, but that's what I understand so far. So I was confused when you said block 1 on main node, block 1 on the main node. Hello, sir.
Okay. Sorry. Maybe just a slip of tongue. Block 1 on data node, the blocks sit on the data node. So the name node will be the one to tell the data node that, see, don't work on, I'm sending you to do a job for me. I want to work on this client data. You have access to this data node. You have access to block 1 and block 4, but don't use block 4. You work on block 1, and it goes to data node 2 and says, see, I know you have block 1, 2, 3, but don't work on block 1 because I've already assigned block 1 to data node 1. You work on block 3. So the name node is responsible because the name node has the metadata, is one that coordinates. So you see, he said the act bit and the block report. So it's one that tells them, okay, you go there, this is what you should do. So like what you said, the block sits on the data nodes, and that's that. So data replication, we've talked about data are being replicated from what we saw here. What we see, data replicated from different nodes, the same block, but replicated on different data nodes. And this is just to take care of maybe if there's any failure of the data nodes. Okay, so that's that. So say the data node stores the received block into a local file system and forward the partition of data into the next data nodes in the list. The same operation is repeated by next receiving data nodes until the last node in the replica set receive data. They're like, okay, they keep giving to each other, okay, you take this one, you take this one. So it's just a replication process. So the process replicates the different data blocks across different nodes. Okay, the rack awareness. The rack is a physical collection of data nodes. Like when you have your rack. So most of us, we are used to a loan system. So, but when you get to say IT department of maybe any organization, is that you have a rack and you see different servers. It's just like you have shelves. Yeah, let me just use shelf. So some of us that have not seen it before, just like you have shelves and you have different books on the shelf. So and each book is like a server connected together. So rack is a physical collection of data nodes. So each server is like the nodes that are stored in a single location. So it's just like a shelf where you have a lot of books. So books are nodes and same location. Then large HDFS instance run on a cluster of computers that is commonly spread across many racks. So when you check a rack, you can see a lot of nodes. Like when you see, you guys can Google, I know most of you must have Googled, let's say Google data center. You see how they arrange racks, and on each rack you can see like say 10 nodes, and on you're having like say 50 racks. So that is the HDFS system, and you have a process managing all of them. It said the network bandwidth between machines in the same rack is greater than network bandwidth between machines on different racks. So I think we can understand that. The name nodes determine the rack ID that each data node belongs to. There they are group rack awareness. So the name nodes, that guy called name node is doing a lot of work, because he's the guy housing the windows called HDFS, and that guy needs to keep track of everything that is happening on the data nodes. Aside the data nodes, also what is happening on the rack. So on the rack awareness, the master node understands rack, he understands the rack ID, he knows how many nodes do we have, how many data nodes do we have on a particular rack, he knows how many rack are we having on this file system. So he knows that, okay, we are having 7,000 racks, and on each rack, he knows the ID of each rack, and he knows the corresponding node on each rack. So that guy is doing a lot of work. Said an optimization of a rack awareness policy is to cut inter-rack write traffic. Like, how do those racks also communicate to each other? So we understand that nodes within a rack, they communicate better because they are within the same network. What if racks are disjoint? One rack can be in Lagos, another rack should be in Abuja. In where I'm working, like the project site I'm working, they have a data center in CMS. They have another data center in where? Ikeja. I think they have like 3 or 4 data centers in Lagos alone. So all those data centers, they are like independent rack. Like maybe each location is like a rack having different nodes. So I'm just giving us a pictorial ground. So if a particular guys within say CMS network, processes within CMS network will run very fast. But when CMS network is now trying to communicate to Ikeja network, and they are reading and writing, maybe they are reading and writing via the internet or via a particular network, it's going to take time, because at least there's a router that is doing the receiving and the sending. So there's going to be a little latency. So to minimize global bandwidth consumption and real latency, HDFS try to safety a read request from a replica that is closest to the reader. So I hope we are getting a picture. We are trying to paint how HDFS works. So if a system initiating the read, the system will check which replica is the most closest to the system initiating the read. Okay, let me say I am in CMS. I'm working from CMS branch, and I want to read a file. Whereas the file I want to read is replicated both on CMS server and Ikeja server. So anytime I initiate a read, the system understand like, okay, which replica is closer to you. They say, okay, you're already you are in CMS. So we will just say, okay, we have a replica for you on CMS network. So you just work with that replica. So there will not be a need for for the system to go and pick replica to read a replica on Ikeja, because it's going to discover that there's going to be more latency. So those are the processes that is put in place. Each data node periodically sends a heartbeat message to the name node, which is used by the name node to discover data node's failure. So they communicate heartbeats like pam, 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 in microseconds to tell you, see, I'm available. Like it's just blinking, I'm available. If you have a job, I'm available. Anytime the heartbeat doesn't connect, the process is reshuffled and miss the other nodes. The name node marks data nodes without recent heartbeats as dead, and does not dispatch any new input or output request to them. HDFS supports traditional hierarchical file organization similar to most of the other existing file systems. So files are in hierarchy, owner, first user or secondary users, and the likes. So, okay, now let's check. Since the data is replicated thrice in HDFS, does this mean that any calculation done on one node will also be replicated on other node? Discuss. We're having 3 minutes to discuss this. Richard, discuss. Richard.
Mr. Ivan, understand the lecture. I really don't know.
What did you say?
I'm also trying to understand the lecture. I really don't know for now. So.
Okay. Okay. So now, so the rule of my class is when you don't know, you call a friend. So I won't be the next person to call a friend. So you call a friend. So if your friend does not know, you've used up your lifeline. So call a friend.
Okay, I call Daniel.
Daniel. Daniel. Is Daniel on this call?
I am. Yes, I am.
Okay. Somebody is asking you to come and sit on your seat. So we have a question, and the question is very simple. Since the data is replicated on thrice on the HDFS, does this mean that any calculation done on one node will also be replicated on the other 2 nodes? So that's the question. So what's the answer?
I believe since the data is replicated on, I'm trying to read the question again, so I'm very sure of my answer. Since data is replicated twice on the HDFS, will the calculation be done on other nodes?
Call a friend. Yeah, guessing.
Okay.
You don't know.
I'm not sure.
You are not sure.
I don't
So
say nothing wrong.
call a friend. The answer is just yes or no. So
okay.
Call a friend. So you guys should be scared of people to make friends with. Oh.
I'll say no, actually.
So why do you say no?
Well, replicating the data on other nodes means more process.
Okay.
It means more process. Okay, let me call a friend. I call Adetoro.
Adetoro.
Hello, sir. I'm here, sir.
The question.
I didn't hear what you said, sir.
Adetoro.
Sir, I can hear you very well.
You did not hear my question, right?
Oh, no, I thought you said something.
No, I didn't say anything. Answer this question on your screen. It's a yes or no answer. And I don't want guess. I've been talking since morning. And you come here to tell me yes or no answer. Okay, no worry. All of you, assuming we are in a practical class, I'll just say, all of you, stand up, raise up your hand and close your eyes. But don't worry,
Sir, can I call you as my friend? You're my friend.
Okay, that's a cheat. Okay. So like I'll just answer it in 1 minute.
Thank you, sir.
When we are explaining, let me go back. I just want to go back so that we can understand. These things are very simple. I said something when I was explaining this data node. I said the name node will tell data node C. We tell data node 2. See, I've already assigned the task to node 1. You don't do it. So each node, the process is not replicated. The name node is in charge of saying, okay, it is this task should be done on this name node and on this block. They don't work on multiple blocks. They work on one block. One block is worked on once, just on one node at a time. So that's the question. So the answer is, does this mean that any calculation done on one node will also be replicated on other two nodes? No, it will only be done on one node. So it's only when maybe the working node fails, then the next node will pick it. But if the node that is working on it is still active, they are going to give it that right to finish the work. But if peradventure during the process it goes down, the other nodes that has replica will pick it up from there. So that's it. Fine. Interesting. So
okay, I want to ask a question.
All right.
If it has already done the process and it has stored, will it replicate immediately? Just to be sure.
If what?
If the process has already done calculation and has been completed, with
Yes.
that new process has done, the new updated node, will it now replicate it again on other? Will you replicate it again?
No. When you give a job, let's say a MapReduce job, and you tell the master, because it's the master that is coordinator of them with the help of Yan. When you tell the process, I want to perform a computation on a particular file system. The file system is 100 gig, or say 1 gig. And we should get that the 1 gig is splitted with as blocks on different nodes. If the computation is done, that job is done. It's just like they've killed the job. So far, the system gets the reports. They've killed the job. It's like the job is done. So if you initiate another process, they can now redistribute to different nodes. So there's something. One of the disadvantages of HDFS is that it doesn't catch results. So when they finish the job, that is, I want to say it in Yoruba, that case is closed. So they see each job independent, and by the time they are running the second job, if you run a select statement, say select star from a particular table, the node that gave you the report now might be different from the node that will give you the report the second time, because they are done independently. The result, as you said, is only sent to the master, and it is kept there pending the time it is being used. But if the request is initiated again, the master redistribute and get a new result. So each request is independent of what happened in time t-1. So let's go.
Thank you very much. Let's start now.
Please. Okay, please, we have a lot to do. Please just type your question on the chat. If you have a question, please type it so that I won't be going. I'm just having like a few more minutes to go, less than 1 hour, and I want to be able to cover much. So I said an instance of the file system object can be created by passing a new configuration object into constructor. I said if execution is done on the remote machine, the configuration file system must be explicitly added to the application class. Okay, before we get there, the fifth objective here said, okay, let's start from the top. Said access to HDFS is through an instance. of the file system object. A file system class is an abstract-based class for a generic file system. So when you have a file system, so like there's always a generic file system. That's why the process you run at time t is independent of what you run at time t minus 1. And that's how it goes. So they always have like a file system that is a bit generic with respect to the process that you are currently running. Is that it may be implemented as a display file system or a local one that uses the local connected disk. So you can have it can be implemented as a distributed file system, or you can just have it on one single machine, one single hard drive. An instance of the file system object can be created by passing a new configuration object into a constructor. So you can set up a new instance, like setting up a new name node. So you just need to pass in a new configuration object to say, okay, see you. This is the channel, or this is the port I'm opening for you, or this is the new machine I'm bringing up. So we are going to understand this part when we maybe by the time we have our practical class. So I hope that maybe at least one lecture in a week will be our practical lecture. So though, as this class is, maybe out of the 3 lectures in a week, maybe Friday lectures will be practical moving forward, so that I have a hands-on class on this, and you can see how it works. And it's very simple. The execution is done in the remote machine. The configuration file must be explicitly added to the application class path. What we read earlier, one of the disadvantages of HDFS is that you can't just bring any application to interact to HDFS. It's not like that general application. So for any application to interact with HDFS, there's a file path you need to set. There are a lot of configuration. So that's why in time past, I remember like maybe 2 years ago or early last year, one of my senior colleagues, when we are trying to install, I think I told you earlier, when we are trying to install Hadoop on Windows, it was hell. But by the time we finished installing it, it was interesting. The reason being that you have a lot of configurations to set. If your paths are not rightly set, your Hadoop system will not connect. So and you as a data engineer, your work is to be able to set up a working Hadoop environment and to do a lot of things. So we'll be getting hands-on on our practical class. So the following code snippet shows how to create a file system object. So file system. So in our practical class, you see what they call the configuration file and other stuff. So a path object can be created from a string representing the location of the file directory on the HDFS. Okay, so we see that more in the practical class, and you understand that. So Novasoft has knowledge check. Novasoft has 10 nodes Hadoop cluster. The name node starts behaving in an erratic manner. The administrator therefore has to format the name nodes. What are the precautions the administrator needs to take? Question. So the question is, when you are formatting a master node, the name node start behaving, the name node, that is the master name node, right? The administrator therefore has to format the name node. What are the precautions the administrator needs to take? So any question, okay, let me answer this question, and I will take in your question because we still have at least 1 or 2 resources to go, presentations to go. So when you are formatting when you're trying to reset the name node, you must be sure to keep what I call the metadata on the name node, because that is what stores like the configuration file, the part that each of the name nodes can be identified with. Like the metadata of the node must be secured, because when the name node is coming back, you just load the metadata and the system can continue from there. Okay, in addition to ordinary file, HDFS also introduced several specialty file types that provide richer functionality for data processing. Sequence file provide persistent data structure for binary key value pair. I've said are also available in append-only format. You know what they call append? Just add up. The use of sequence file provide a storage mechanism natively supporting key value structure, thus implementing using the data layout much simpler. So it said key value. So the key value is that each file system, there's a value, there's a key to each door, to each file system, to each data block. There's a corresponding tag attached to it. Sequence file system has 3 available formats: uncompressed, record compressed, and block compressed. So and this is part of the functionality that makes it optimize space. So far you can have it in the compressed format and both the block format. So we're having 3 presentations. Okay. Part 2. So now we are going to understand the record compressed file. So when you have the header, the record. So the header is just like your table names. Like you guys that write Python, just like column names. So the column name of a data frame. So you have the header and you have the record. So this is what we call record compressed sequence file. So there's a sync. So moving forward, you don't need to always have the total table structure again. The table structure needs to be kept somewhere, but the other file, so far okay, let me bring it make it more clearer. You have these guys, record compressed. So each record, like each rows, they are in sync with each other. But in block compressed, each blocks, when you have like the way we have different blocks. Okay, I want to reiterate something. In a particular block, you can have multiple records, but in a record, it's just one single record. So just like one single entry, that's a record. But in a block can, our block size is 64 MB. So 64 MB can have like say 1 million rows. But in our record compressed, it's just per record. Each record is identified and they are keeping sync that but all of them communicate to each other. All formats use the same header, like what I said, yeah. So the header are in sync. They're like using the same header and everything is they're able to, when you break blocks into pieces, when you break a data file into pieces, like say 1 gig, or let's say a table containing say 1 million rows, and you break down 1 million rows into say 5 blocks. Each blocks will still make use of the header name. Said if compressed is enabled, the compression code class name field is added to the header. So each header each block has the same header. The metadata for the sequence is a set of key value text pair that can contain additional information about sequence file that can be used by the file read and write. Okay. I'm looking for a way to explain, but I know we understand better with time. So also, a special reader and a writer are provided by Hadoop to use the sequence file. So when you are reading a file, some slides back, I said something about key value pair that I said, see, each file, each data block has a key value pair. So the sequence file too is also like an index that comes with every block, such that when you are reading, it knows it is equivalent to what they call on Oracle, we call it indexing. So you can have a table and just create index on that table, which will enable you to easily access records on that table, or what we call partition. So corresponding word for partition there is what they call the sequence file that gives easy access to the reading of the data file and the writing. So the following code shows how to use sequence file. So this will be best appreciated on practical class. Okay. So you see, one of the limitations of sequence is the inability to seek based on the key values. Indexing generally across all, I think my experience with Oracle is that when you index a table, you can easily select from it. But when you are inserting into it, it takes time. So that's the same situation here. One of the reasons of sequencing is that inability to seek based on key value pairs. The map file is a directory containing two files. Data file, when you have the data file, so when you talk about the map file, data file and the index file. So the index file is the one that tells you, see, I have record 1 on this block, and this is the exact location on the disk. The map file are typically used to enable an efficient search and retrieval of content. Yes. So you have the key offset. So the key offset will say, okay, where is this file? Just like when you go to a library and you go to the shelf, before you go to the shelf, you go to the catalog and say, okay, please, where can I find this book? And they give you the key. Go to shelf, so, row 1, number 2, you get the file there. So that's what the map file does, which is a function of the key value said is a function of the index of the index and the key value. So just like one is coding and the other is decoding. So they have the pair, a key that say, okay, when you want this is what you use to access it and use it for retrieval. So it's just like a communication portal that give easy access and that enables you to easily get data out of or process out of your database. Write to open a file, so as part of Hadoop, blah blah blah. So this will be our practical class question. So the federation. Part of what we said we'll be talking about is the HDFS federation. HDFS federation, and have anyone of us heard of what they call federated table before? Have you heard of what they call federated table? Have you come across the word federation as federated table?
No.
Okay.
No.
So in my SQL, if you want to connect two databases together, those databases they are sitting on different servers. Even if they are sitting on the same server, but let's say two different databases, and you want to connect them together, such that you want to be on one database and be accessing what you have on another database. There's a table you create, they call it federated table. So you create a federated table for the corresponding table that you want to work on. So, but in this case, all the file metadata are stored in memory. That's one attribute of federation which related to Hadoop. The metadata, they don't sit on hard disk. Now I'm saying they sit on memory. So that it can be flexible for the master node to communicate seamlessly. And so that, the reason why we do most of our things on memory is to reduce latency. So that when they ask the master node to go and do something, it's not going to be taking the master node a lot of time. And you understand that communicating to any table, to any block of files or file block on the data node, the name node needs to have access to the metadata to communicate. And if it is taking the name node long time for it to communicate with the metadata, then communicating to the data node will also take time. So all the metadata sit on is stored on the memory. The amount of memory in the name node define the number of files that can be available on the Hadoop clusters. So that means our name node must have a sufficiently large amount of memory. So overcome the limitation of a single name node memory and be able to scale the name service horizontal, Hadoop 2 introduce HDFS federation. So now, HDFS 2, it is when you have two masters controlling them, so that in case one of the master fails, the other one will pick it up. Federated is like you are connecting two systems together. I made an example of MySQL. MySQL is connecting two databases together. But in Hadoop, you are having two master nodes that have the ability to control all the, say, 5 other data nodes. But so he said, the distributed file system, the Hadoop 2 introduce HDFS federation so that we can have two masters, no longer one. Because if one fails, the other will pick. And all the information on the active master node is in real time replicated on the slave name node. That slave name node is on standby. As soon as the active name knows has maybe any failure, the guy picks it up. It said HDFS federation is based on multiple independent name nodes or namespace. Following are the benefit of federation: namespace scalability. HDFS cluster storage scales horizontally, but the namespace does not. So the namespace is like the name node. Okay, I have a message. Okay, somebody said, Adedeji, is the network breaking? Are you guys hearing me clearly?
Yeah, I can hear you.
Yes, I can
My
hear
voice
you.
is
Yes, I
clearly.
can hear you, sir.
All
So
right.
please can you expatiate on namespace scalability and explain what it means for it to be horizontal.
Okay.
In the previous slide.
Okay. So namespace. So now I'm referring you to the namespace as the master name node. Okay. From our previous methodology, we've been taught that you have one master and you can have, when you have one master, or you can have multiple name nodes, multiple data nodes. That is vertical. But when you talk about horizontal, as you are increasing vertically, that means you are adding data nodes. You are also adding master nodes. So you are not only adding data nodes, like having like 50 data nodes, but one name node. But as you are adding up data nodes, you are also adding up the namespace. So that each namespace is like one namespace is like a data node and the corresponding name node. No, a name node and the corresponding data node, like a master and the corresponding slave. That is vertical. But when you are increasing horizontal, you are having multiple name nodes, and yet you are increasing your data nodes. So that is horizontal. So now we are not working on one master again. What if that master fails? The last, some questions back, like one of the questions we were asked, the question says, what happens if a particular name node is behaving somehow and you need to format it? So in that case, it is best you have a federated architecture whereby you have a standby master node that can pick up the job. If you are in the cloud, if it is in the cloud that you are setting up this, or if you are setting up this kind of architecture in this cloud, with just one click, you can just set it up and say, okay, if my master node fails, I think this is more applicable to relational database. If the master node fails, the next available slave will pick it up. That is what happens to relational database in the cloud. But in HDFS architecture, especially Hadoop 2, before it goes down, there's another guy that is scaling horizontal, that in case even my master node goes down, this guy picks it up, and my process will still run seamlessly, and there won't be loss of data or loss of information. So that's horizontal scaling.
Okay, so sorry, before we leave, I want to ask a question. Sorry. I just want to confirm what's in my head, because all of this is abstract. I'm just trying to paint the picture.
Okay.
When we talk about HDFS federation, we just talked about multiple HDFS systems or models, whatever, coming together to perform a certain kind of task. Now, I'll go down to the okay, because I'm also saying that name nodes, namespaces, a couple of namespaces make up HDFS, and then a couple of HDFSs make up the HDFS federation. Yes.
Yes.
Okay. I just wanted to confirm that hierarchy.
Okay. So let me reiterate that a namespace, let's say a namespace as one namespace as one name node and multiple data node. That's one namespace. When you want to have, and that namespace is one Hadoop distributed, so it's an Hadoop distributed file system. So all those, the name node and the data node, all of them sits on Hadoop, right? So that's the namespace. So when you don't have two of them, like say you have two masters still sitting on this, it's just as if I was telling you that I said, see HDFS as a window whereby you can scale, you can have different applications. the first file system that was built as one master and multiple data node. With Hadoop 2, you can have two masters and multiple data nodes. So one master and multiple data node can be classified as one namespace, and the second one will be another namespace. So that's that. Okay, I hope I'm not confusing you.
No, thank you very much, sir. You made it very clear. Thank you.
Thank you. So, okay. How many of you guys has this material? You've gotten your material.
90% of us, just one person from Port Harcourt doesn't have it.
Oh, so you guys are good to go. So that means you guys can go back to others. So we just need to do a little bit, just go a bit, we increase our pace a bit. Okay. So you guys can go back. When you have any question, you come back, then we'll solve it. The figure below shows the implementation of HDFS federation. So, name node 1, name node 2. So in this case now, we are having multiple masters. Multiple masters. And all those masters, they are managing the same sets of name node. But there's something that is common to them. They are pool. This let me see. This box here, this block of pool is like they are, you know, when we talked about parallel computing, they share the same memory. So that is what makes them communicate in sync. So if name node 1 is working, he understands everything that is happening on the data nodes. If name node 1 now fails, and name node 2 is picking it up, name node 2 can also share in the information gotten from other name node to control name node to control the data node. So they share the same block of pool. So all of them, they share the same block of pool. Because if they don't share the same block of pool, it will be difficult for, okay, let me say it this way. You have a manager and an assistant manager. A manager oversees like 50 team members, and one day the manager is sick. Maybe during his operation, he doesn't carry the assistant manager along. Like, he just goes to work. The assistant manager works in isolation. He doesn't know anything that is going on. Any day the manager goes, maybe falls sick, and the assistant manager is to take up, he will find it difficult to manage the team. Like, he might be reassigning some task irrationally. But if the manager and the assistant manager are in sync, they are sharing the same information. They're like, okay, CEO, yesterday I gave also Mr. A task to do. So the guy also put it in memory that, okay, task A is given to this person. So that anytime the manager is off work, the assistant manager can pick it up seamlessly and still manage the entire team as if nothing went wrong. So that is the implementation of HDFS federation. Okay. The namespace operates on a set of blocks known as blocks pool. Each block's pool is managed independently, which allows the namespace generate block ID from new blocks pool without the need of coordinating with other namespace. The failure of a name node does not prevent the data node from serving other name node. So that is the interesting thing. The failure of a name node, the failure of a manager does not prevent the team member to serve other managers. When a name node, so that's why I said a name node / namespace is deleted. I said something the other time. I think this line is making it clearer to say A name node is the process in a name node is equivalent to what they call a namespace. That is, when you have a masters, it controls different data node. When you have a name node, it controls different data nodes. So that process is what I pictured as a complete namespace. So, but in this definition, we are equating a particular name node to a namespace. But don't forget that what makes a namespace complete, you must have corresponding data node. He said, if a name node is deleted, the corresponding block pool at the data node is deleted. Is this, is point 2, 3, and point 4 not confusing? Can somebody justify this point 2 and point 3? Point 3 said, failure in data node does not prevent the other nodes. But this one is saying, if a name node is deleted, the corresponding block at data node is deleted. So that means failure is different from deletion when you delete. So when it fails, a work is passed on. But when it is deleted, the whole architecture, because when a name node is deleted, that means the metadata on that name node cannot be recovered. It's just as if you perform a transaction and you generated receipt, and your company wants to reimburse you, and you just said, "See, my receipt has been, I misplaced my receipt." They said, "Okay, we can reimburse you." So if the name node is deleted, the metadata on it goes with it, and with that, it will not be able to communicate with all the data node. Okay, HTML Federation configuration is backward compatible and allows existing single name node configuration to work without any change. Okay. Okay. So we have a beautiful picture that tells us more. You have two servers, two name node. This name node can interact to all other name nodes, and this can interact with all other name nodes. So in case if one fails, the other comes up. But they share the same storage. There's a functionality in the cloud whereby you can have, and that is like the file system infrastructure in the cloud. You can have multiple EC2 instances connecting to one storage file. And that's what is happening here too. Each name, they are all connected to. So that is why if one name node fails, like if one namespace go bad, the file is not missing. Just like this guy is disconnected. All this name node will take care of the operation. So far, the data is not stored on any of the name node. The process just continues. The active name node is responsible for all client operation. So keep the state of both name nodes in sync. The implementation requires that both name nodes have access to a directory of shared storage, and that's that. So this is the high availability architecture. Okay, module system would like to ensure high availability. What steps should they take to achieve this? Just make sure they have two name nodes, and all the two name nodes have a shared storage. Okay. 11. H base. So the H base. So to me, the H base is like the server. Is the guy that keeps the file. So HBase is a distributed version, column-oriented multi-dimensional storage system designed for high performance and high availability. So you can only appreciate HBase or understand the column-oriented table if you've worked more on relational databases. So, but we'll go. Maybe in our practical class, we'll spend much time on this and we'll try and get answer to it. We have the HDFS. That's our Hadoop distributed file system. So on this Hadoop distributed file system, we have servers. We are not, assuming we are in class, I will have make this clearer. These servers, let me see them. I want to see them as cluster of nodes being monitored by one master. So this master is managing this guy and managing this guy. So from the master, a master sends a query through a client to the region. Say, select age. I want to assume we have a lot of data files here on the regional server, and there's a query that was initiated by a client to this master. And the query is select star. Say, select age of student in DASCA class. So when this client initiates, this is a client, like this client can be an application, like OZ or Scoop, or even Eclipse. It can be a JavaScript file. You initiate a request through the master. When you initiate the request, Zookeeper is like the guy that understands how the process goes and sends a corresponding well-detailed information to your master so that your master can visit any of the servers to get the data. So when this is done, your client gets the results back. This looks abstract, very abstract, but it is simpler than what you are seeing. When we get to the practical class, find that it is more simpler than what you are seeing. Okay, let's move forward. We'll deep dive with time. And then the architecture of HBase. One thing is HBase is a column-based and multi-dimensional table. Okay, we have our practical class here. HBase is an open source implementation of Google big table architecture. Similar to traditional relational database management, data in HBase is organized in tables. And another thing is it supports a very loose schema definition and does not provide any joint query language or SQL. So HBase is like loose schema, like well disjoint. The query, though you can run Hive on it, but it supports like it's well disjoint that when you see the architecture, starting from the family of the table and the other attributes, you see that it is disjoint. You can and that is why you see all our queries and our search engines very fast, because all the queries, all the attributes we are looking for, they are well disjointed. Well disjointed. The main focus of HBase is to create, read, update, and delete operations on wide sparse tables. Most HBase implementations are highly denormalized. Similar to HDFS, HBase implements master-slave architecture. So keep that in mind. HBase implements, it has its own, like the way we have master and the slave, the name node and data node. The same architecture works for HBase too. But you understand that HBase is mainly for storing data. HBase leverage HDFS for its persistent data storage, and also we said the regional servers implementation consists of the following major components, which are memstore HBase implementation. That is like in-memory data cache, which allows improving of overall performance of HBase. By serving as much data as possible directly from memory. This is better understood with practical, but just keep it in mind that HBase, Hadoop, HDFS itself does not cache on a standalone system, but Hadoop, it does its own caching on memory. So that's one difference. So I won't mix it up in the exam. I say, okay, they said, okay, Hadoop does not cache into a standalone system, but HDFS, it caches its own memory so that for easy retrieval. H-file is a specialized HDFS file format for HBase. So you see this better, and this is where you understand the blocks, where you see the H files in Hadoop system and across the directory. So when you have a logical table, HBase use an auto-sharding and distribution approach to cope with a large data size, and that is when you talk about block, like the same Hadoop HDFS block, when you break your data file into different block. So when you have a logical table partitioned, they are partitioned. So from the partition table, two partition table can be on one. To me, I want to call the regional server like the name node or the data node. So let's say the data node. If the partition tables, like these two partition tables, they are sitting on the same, they can sit on the same data node, and whereas the last partition can sit on another data node, and you have your client querying one table from two different data nodes, and that is the HDFS architecture, where your client can query from both the first server and second server, which I'm picturing like a data node and corresponding data node. So to store a table of arbitrary length, HBase partition this table into regions, with every region containing a sorted a primary key continuous range of rows. Okay, so better defined and for us to have a more defined picture in context of HBase. In context of Hadoop, blocks are put in, data blocks are put in different data nodes are being replicated. But in HDFS, in HBase, you don't replicate. I'm trying to have a two-dimensional picture of the relationship between Hadoop and HBase. In HBase, HBase has, instead of data node like we have here, so I said earlier, I said your region server is like data node in the context of Hadoop. Sorry. No, I'm coming. No. Okay. In the context of Hadoop, Hadoop partition blocks into data nodes. In the context of HBase, it partitioned them into what they call region. So your region is sitting inside a data node, but a region is just like a partitioned table. A region can have more than 2 partitions, like what we saw in previous slide, and your client can work on them concurrently. The region size exceed the, if the region size exceed the predefined one, the regions automatically split. So to each region, there's a specific size. Like we used to say that the Hadoop file system, the maximum size is like 64 MB. So if it reaches that limit, the region too breaks up onto a smaller region size. So the essence of all this breaking, all this distribution, all this partitioning is so that we can access each file to the most granular detail. Okay. The figure below shows the HBase leverage, a specialized table to resolve a specific key value pair to the specific region server. So Zookeeper takes a job. A job can be, a Zookeeper creates all the data definition language, either data definition language and data manipulation language. So when you take a Zookeeper, you run a query, the Zookeeper will go to the root and pick the metadata, the structure, say, okay, data I'm looking for is in a particular table, and on which region can I find it? And you get it done. Please, sorry, give me 1 minute. Sorry for the break in transmission. I just need to attend to something. So the zookeeper takes a query, goes to the root. You should understand that on which of the server is our metadata sitting on name node or on data node? I need that answer now. So on which server, on the data node is our, on which of our server is our metadata sitting on? Is it sitting on the data node or the name node?
Name node.
Name node. Okay. So the zookeeper, yes. Thank you. So the zookeeper interacts with the name node. So anytime you see the metadata, you understand that our name node is the one coordinating it. Then it's pleased to say, okay, where is the job? Where can we find the data, which region, and what's the corresponding key value we can use and the like. So there are a lot of background processes there. So, and also the following figure shows H-based tables as a sparse, distributed, persistent, multi-dimensional sorted map. Please, I would explain this better when we are in our practical class, when we create table, when we load data into our table, we will get to understand this. We get to understand this. Okay. So data operation in H-base, by default, H-base stores at least 3 versions of a given column value. Sincerely, you all see this. Oh. Are you guys having access to your online school material, data science school?
No, sir. We're yet to have access. We don't have access yet.
You don't have access to data science school. Okay.
Well, we have the materials.
You have the material. So okay. So when we get to the practical class, we'll understand what they call versioning. H-base is the first time I got to interact with H-base, I know H-base is a multi-dimensional table structure, whereby you have the row, you have the column, and the third dimension of H-base is what we call the versioning. So, and the versioning is a function of time. So just like you have a 3-dimensional plane, the first dimension is, let's say, the row ID. The second dimension is columns. Even H-base can work on 4 dimensions because on a particular row ID, you can have a particular family. On a particular family, you can have attributes. You can have multiple attributes. On those attributes, you can have values. And on those values, you can now have versioning. So these are things that make it very easy. When you do something on a multi-dimensional table, you can easily pick, okay, this you just need to specify where, then you get it done. So the following are the 4 primary data operation. Get. So get is just like select, put, insert. Get is also scan. It's also going to help you to select multiple records. So you see that scan allows iteration over multiple rows for specific values. Get return value of columns family. You understand this family when we are in a more practical class. So delete removes a row or any part therefore from a table. So that is that. So please you bear with me. I think we spend a lot of time here. So in our next class, we'll be starting with the part 3, and what we'll be doing fully then will be practical. What we'll be doing then will be practical. Then we'll be going through, I wish I'm looking. So then it will be a practical session. I think that will give us a grasp knowledge. So that's that. So I might not be able to take us through. So this is just a summary. So what I would do is on points to remember, I will take a screenshot of this session of this point to remember and paste it. We can all go through it, and so that we can just go through it to understand what are we to understand about getting data into HDFS. And our next class, as I promised, is going to be practical. I can see that it is simpler than what we think, though we have a lot of abstract jargons. But when you go to the practical class, it's more simpler. I can easily understand. So I'm going to take a screenshot of these guys and paste it on. So I know some of us, we have access to the material, but at least Iyola, your camera is on.
Trying to check messages.
Okay, do you have any question before we call it a day? Any question?
There are some questions.
Okay. What's the question? There's a question on?
In the chat box.
Okay, let me check. Okay, can we call HBase a NoSQL? Yes. So, because you don't run the normal SQL query on it. So, and it is not relational, like our normal relational database. So we can call HBase a NoSQL database. So, okay. So I think somebody's commenting, say, I think vertical scalability occurs between name nodes and its data node, but horizontal can have multiple names. Okay, that's fine. This is also the reason why HDFS federation does not affect horizontal scalability. Okay, that's fine. So who is this guy, admin at Octave Analytics?
Sorry, I think that's me. I don't know why it's Hubert.
Is obvious. Okay, all right. Yes. No problem. So guys, thank you very much. Please, you can chat me up personally to ask any question. I will answer. But I would like to call it a day.
So please, how do we chat you up? Come back, please. How do we chat you up?
How do you chat me up?
Are you going to like drop your number or?
So okay? Can't you guys interact? Okay. Can't you guys interact with us? Can't you guys interact with us on Microsoft Teams?
I do not think we have that privilege. We only access the classroom. So.
Oh. Okay. So let me give my WhatsApp number. So I will be available.
Okay. Thank you very much.
All right. Thank you, Emmanuel.
Saidi.
Baba. Currently I pasted maybe just for just page 12. Please help me snap screenshots page 13 and page 14 on the group so that they can all see. That is points to remember. So thank you everyone. Nice meeting you guys. We see next week Monday.
Thank you very much, sir.
All right, thank you guys.
Now, I did say I'm busy. Say I'm busy. Network now is still here. I cannot hear our TikTok. I cannot hear our trainer.
SMH. Just be aware.
It's fine. Yeah, it's fine. You're right. Everybody should be to class. I think.